Okay, welcome everyone. We're very pleased to have Zechuan Zheng from Paris, who's been working with Volodya Kazakov, and he will tell us about the large N matrix model Bootstrap. Please take it away.
Okay, do I start? Okay. Hello everyone. I'm going to discuss my recent work with my supervisor Vladimir Kazakov on the large N matrix model Bootstrap. So, what is large N matrix model? It's models defined by the following partition function. It is integration over different matrix instead of the scalar variables we deal with in the traditional integral. And it has many applications like metascopic physics, two-dimensional quantum gravity models, statistical mechanics, and on the planar graphs and 2CD. And this work is about solving large N matrix model by Bootstrap method. So let's briefly revisit what Bootstrap method is. From my point of view, basically Bootstrap method is a method that trying to solve the theoretical physics problem by the optimization theory. Let's see, I gave several very simplest example of optimization theory, like the quadratic programming. That is, you minimize quadratic polynomial. Yeah, you just minimize a quadratic polynomial. And linear programming, that you minimize or maximize some linear combinations of some variables subjected to some linear inequality. This is what we have learned in the maybe junior school or high school mathematics class. But this is not as trivial as it seems, because suppose we have like 10,000 constraints, it will be very hard to solve it accurately. Today, the optimization problem we are going to dealing with is semi-definite programming. We are going to minimize some linear combination of variables subjected to some semi-definite inequality. That is semi-definite positiveness of a matrix. Actually, the linear programming and quadratic programming we just introduced, there are special situations of the semi-definite programming. They all fall into the class of convex optimization. You can check that all our constraints, they are convex. Generally, we cannot solve a large-scale non-convex optimization problem. They are actually, sorry, yes?
Sorry, what does that constraint mean? A matrix is bigger than a number?
This constraint means this matrix is positive semi-definite. All its eigenvalue, they are larger or equal to 0. Is it clear?
Yes, thanks.
Okay. Generally, we cannot solve a large-scale non-convex optimization problem. They are in the sense of computational complexity. They are NP-hard actually. So let's see how Bootstrap method works on a simplest Bootstrap model. Let's just consider the single variable integral. This is a quartic single variable integral. An integral non-Gaussian, of course. And we demand that the g here is larger than 0. What we want to compute? Well, we want to compute this case moment, that is x to the k, integrated all against this positivity measure. We have, of course, we have a lot of choice to do the integration. We even have the analytical results. Okay. Can anyone mute themselves? Okay, we even have the analytical results for this moment actually. But for the Bootstrap method, we are using 3 basic ingredients. That's called the loop equation, global symmetry, and the positivity of correlation matrix. Loop equations, they are just a stringer Dyson equations, or if you prefer, they are just integration by parts. By the loop equations or by integration by parts, we can relate the different moments by the loop equation. And we also have the global symmetry that WK equals 0 for all the k. Global symmetry, this seems very trivial in this case, but they are actually independent from the loop equations or the series of equations from integration by parts. So for the numerical efficiency, we better impose it. So after imposing the loop equations and the global symmetries, we can see that all the higher moments, they are linear functions of W2 actually. The key of the bootstrap method is that we can also considering the expectation of square of polynomials. Of course, they are always positive. They are always larger or equal to 0 because you are integrating a positive definite functions against a positive measure. So it is of course positive, and we can expand this integration in terms of its vector of coefficients. So this is in terms of alpha. Alpha is the vector of the coefficient. This integral is a quadratic form actually. So its positive, the positivity is equivalent to the positivity of the matrix of the quadratic form, where we call this matrix correlation matrix. It is a matrix, actually it's in the form of Hankel matrix, and all its elements, they are just some moments. We know that it is positive semi-definite. So we have actually it is an algebraic inequality on W2. So we want to know that how this works. We can use the semi-definite programming we just introduced to solve the minimization or maximization of W2. Well, of course, if we want to implement numerically, we need to select the top, let's say, the top lambda plus 1 times lambda plus 1 submatrix of the correlation matrix. This must be true, but does this really work? Actually, it works. We have the we have the analytic result that's actually by some modified Bessel functions in terms of k and I. For g equals 1, we treat this as a generic value of the g. We can get the numerical bootstrap result and compare with the analytical result. We pick cutoff equals 10. This means at most we consider the W20 in our correlation matrix. And we see that we get 5-digit precision here. So this bootstrap method, it actually works and works well. We also have the allowed region for general G.
Sorry, can I just repeat? What is the idea? So you have loop equations which relate moments of different powers.
Yes.
Different moments. Then you can build. Sorry, and the information about the potential is already encoded into 7, right?
Yes, the information of the potential is in the loop equation or integration by part.
Right, and then so you express everything in terms of W2, you said?
Yes, yes.
And then require positivity of this matrix, you get bounds on W2.
Well, the positivity of this matrix, they are just a series of algebraic inequalities on W2.
Yeah, so you impose positivity to get bounds for W2. That's
yes.
But then why should this bounds be narrow?
Yes, this is what we are going to discuss in the following. It actually works. I mean, the bounds could be totally trivial, but it is not actually. It gives us very tight bounds.
What's the asymptotic of W with index k as function of k?
Sorry?
What's the asymptotic of WK as function of k?
It is linear functions in terms of W2. If you are asking the asymptotic, I think I didn't try to solve it, but I think you can try to solve it by the saddle point method, right?
Okay, so I am asking because you are going to truncate, and somehow the question, if these W's are growing, then there will be the question about truncation. But
yeah, the higher it is, more sensitive to W2 actually.
Okay, higher are more important than how to truncate. So if higher W have more.
Yeah, our truncation is just we take the top 11 times top 11 submatrix of this big matrix.
Okay, you can say, for example, that you just restricted for some subspace and
yes.
Okay,
of
that's
course,
fine.
This must be true.
Yeah, that's fine. Yeah.
Yes.
Sorry, and another question: how does n, the size of the matrix, enter into the loop equation?
Sorry.
N, the size. So this was what?
The size. You mean the lambda?
Yeah. So far it was what, usual integral. Sorry, I maybe missed this, or matrix integral.
No, this is just a single variable integral.
And xi is a power. Okay, sorry.
Yes. Okay. So let's
sorry, one more question. The alphas that you had there, how do they enter W2?
Alpha, yes. No. Alpha is any random, arbitrary real vector in the real space. I just expanded. It is a quadratic form in terms of alpha, right? Alpha t times the matrix times alpha. So for any alpha, this is positive. This implies that the matrix in the middle is positive symmetry.
Yes, but later you wrote down an explicit expression for W2.
Yes.
Which in the next slide, I think.
Yes.
Yeah, this does not involve alpha.
Yes, alpha is just in the middle that we derive the positivity of the correlation matrix. After that, we don't need alpha at all. There is no alpha.
Oh, I see. Sorry.
Alpha is arbitrary.
I see. So W2 is just with the x squared, with no alpha.
Yes.
Okay, thanks.
And sorry, and one more question about this formula once it is here. So it looks as 1 over g in some kind of non-perturbative dependence, yes. So in small g limit, how the expansion looks?
You mean perturbatively in terms of g?
Yeah, in small g limit, yes. What's the expansion of this object?
I didn't try that actually. It's an interesting question. Of course, this is a very most of the book in the complex analysis will treat this integral as the example of the asymptotic expansion doesn't converge to the real function. So I think the perturbative result, it won't be very good. But the bootstrap method, the bootstrap method, it works here.
Okay.
You will get at V-coupling just a asymptotic expansion. Base series has a asymptotic expansion at the infinite parameter. So you get some asymptotic series.
Yeah, but some base series, I don't know exactly about this, have also exponentially small terms in one or in this.
Yeah, this I exactly has exponentially small terms.
Okay, yeah. So it is just trans series perturbation series and good.
Okay, any more questions? Okay, let's go on. So let's see the bootstrap in general. That is, in the previous example, we are considering almost the simplest manner. And
but sorry, could I ask? So is for this simple integral, is the statement is that the bounds actually converge exactly to the exact value, or it's just experimental?
Experimentally, it converges. If it could be shown analytically, it converges. We will discuss this problem later. This is one of the main results of this work. Okay. In general, we can consider arbitrarily complex probability matter in the probability measure on the lattice, or maybe in interacting quantum field theory. So the general method is that we choose a basis of operators that they are in some sense complete. Let's remember in the single variable case that the polynomial is dense in some maybe in the continuous in the base of in the space of continuous functions on the real axis. And then we impose some known equality and positivity on these operators, as well as we assume some global symmetries. So numerically, we set some numerical truncation of the bases, the equalities and inequalities. Then we can get some rigorous upper bound and lower bound on the expectation value. From my point of view, this method has several advantages if it gives us good bounds, of course. The first one is we don't necessarily need to know or truly understand the probability measure. That means, I mean this by two meanings. The first one is that we can actually bootstrap the probability measure. For example, there are some recent work on the bootstrapping the quantum mechanics. Actually, they are bootstrapping the eigenvalue of the Hamiltonian. But in this work, they are in some sense bootstrapping the probability measure. And in the second sense, more importantly, in the interacting quantum field theory, we always have functional integrals. Sometimes they are not mathematically well defined, or sometimes they are not UV complete. But most of the time, we still have a lot of equations that we strongly believe that they are true. So this is why then we can get some rigorous bound maybe on some dynamical quantities. And the second advantage is that the symmetry of the problem is easier to implement than other algorithms. The third one is that the most important one, also the most important one, the results will be rigorous. Increasing the cutoff will only improve the bound. Okay, let's go to the matrix model. So the matrix model, again, it is an integration over the matrix. In this case, the loop equations, they are specified by the vanishing of the total derivative, very similar to the single variable case. We want to study the large n limit of this model. That means here the potential is proportional to n, and the remaining term, they are contains only finite independent variable. In this limit, the expectations, they are dominated by the planar diagram.
Sorry, could I ask? So,
yeah.
So before you were speculating about the measure, but if you use the fact the total derivative integral is 0, this assumes a very particular measure which is flat, right?
Yes, but here we are dealing with a matrix model. In most of the case, this is true for the matrix model measure.
Now, just to point out that your speculated measure you don't care about here would bite you.
For more general measure, we might have a different form of loop equation. Yes. Yeah, in the larger limit, there are two very important characteristics that will play very important roles in our work. The first one is, of course, large n factorization. Let me remind you that it is expectation value of double trace operator is dominated by the product of expectations of the single trace operator. And the second is tunneling effect. It is exponentially suppressed. That means we only need a deep enough local minima in the potential to make the model sensible. Let's look at the model 18 and 19. So the 18 one is the model we just dealt with. Here we must have G larger or equal to 0. Otherwise, this is not a sensible model. And for the next model, that's one matrix model. We only need to have a local minima, that is G larger or equal to -1/12. Is there something in the chat? Okay.
Yeah, just please, if you have a question, just ask directly.
Yes.
Sure. So I mean, I'm not an expert in integrability, so I guess this is a very naive question. But what?
Yes. Let me explain it. Let's say double trace operators like trace trace m squared, trace m to the fourth, we consider its expectation value. It is equal to the trace m squared, the expectation value, times the trace m to the fourth expectation value. Is this clear?
Can you just repeat that? I was
Yeah.
It was not clear.
Do I have it in my
Just an operator which is a product of two traces, is a double trace operator. If it's
okay, thanks.
Okay. Okay, let's go on. Let's give some very brief background on the one matrix model. So we consider the following one matrix model. That's a generalization of the single variable case is integral over the particle potential. It is a Hermitian matrix, integral over Hermitian matrix. The most important feature of this model is it is actually dominated by a single eigenvalue distribution. Imagine that we are dealing with some matrix. Matrix has some eigenvalues, and in the large n limit, it will have some infinite number of eigenvalues, and we have a continuous eigenvalue distribution. This is the main feature. How to see it? Well, we can show it by this way. We can represent the Hermitian matrix by its eigenvalue distribution. To do the eigenvalue decomposition, write it with some angle unitary matrix times the eigenvalue matrix. So by this way, if we place this transformation into the matrix model equation 20, we will get the equation 21. We found that the angle matrix, it contributes only an overall factor, and all the dynamical information it is contained in the eigenvalue matrix. So by this way, the degree of freedom reduced from n squared to n. This greatly simplifies the integral. We call this kind of matrix model solvable. So in this case, actually, all the one matrix models, they are solvable.
Sorry, could I ask, will you assume signs of mu and g, so there is a one cut or two cuts distribution?
Sorry?
Will it be in one cut regime or in two cut regime for the signs of g and mu?
Signs of g and mu.
Oh, in other words, g is positive, I guess, right, for you, and the mu, is it
g
positive?
is large. Well, it depends. We will actually in this work we discussed both cases. So here the eigenvalue distribution, they can be both one cut and two cut.
Okay.
Yes. So mu is +1 or -1. So after we reduce it to equation 21, we can impose the saddle point equation to say that the eigenvalue distribution, they are dominated by some specific one described by the saddle point equation, equation 22. So in the larger limit, we can imagine that the integral is dominated by a eigenvalue distribution. Here, the plot is some general eigenvalue distribution. Another important thing I must introduce is the resolvent function. It is actually the, let's look at equation 25. It's a formal power series on the moments, and it is closely related with the eigenvalue distribution by that the eigenvalue distribution, it is discontinuity on the real axis of the resolvent function. Okay, this finishes our very brief introduction to the one matrix model. Let's look at how the bootstrap of one matrix model works. This is a repetition of Lin's work, actually. So let's consider, this is a very straightforward generalization of what we've done to the single variable integral. The basis of operators, they are just some single trace operators. And we have the loop equation here, but there is something different. Because of the Lagrange factorization on the right-hand side, we actually have a sum over the quadratic terms. The positivity of the correlation matrix is exactly the same as the one matrix integral. So this is the numerical result for the for this case. Here we assume that mu equals 1, so there is actually only in single cut distribution. And we also assume the Z2 symmetry, that we assume W1 equals 0. This is a global symmetry condition here. Here, I want to remark that from the loop equation, all the higher moments, they are polynomials of the W2 instead of linear functions of W2. This is very crucial compared to the single variable integral bootstrap. Okay, here I want to make several remarks on this result. The first one is that this bound, of course, they are correct bound, but why they are not totally trivial? Why do they necessarily converge to the analytical solution? Or they don't converge to the analytical solution. They stabilize somewhere apart from the analytical solution. This means, in the other words, I mean, can we justify this condition? We want to understand what we have really imposed by imposing the positivity of the correlation matrix. We know that the loop equations, they are nothing but the potential. What role does the positivity of the correlation matrix play? The second remark is that these loop equations, different from the single variable bootstrap, they are quadratic. By this way, the quadratic equality, they are non-convex. So this is generally a non-linear SDP. But in this case, because of the problems, they are pretty simple, so we can solve them. But generally, we cannot solve the large-scale non-convex optimization problem. So this must be a problem when we consider the more complex models. What's more, all the models in yes?
Excuse me, Zechuan, I'm not sure this audience everybody knows what is SDP. So
yeah, I introduced SDP at the beginning.
Ah, okay.
Yes.
Well, I still don't know what is that.
Still explain what it is.
Okay. Let me remind you. Yeah, in this slide, this is SDP. Yeah, this is we minimize or maximize something, and we under the constraint that some matrix is positive semi-definite. Okay.
Can we see again the plot because it was a bit too fast for the matrix model, just to see. So lambda is a cutoff in the number of power of trace.
Yes.
And then
we see that the bootstrap actually knows there could be some negative G value.
Up to -1/12, up to this G critical, the red point.
So, and then the pink is the best. And does it include all the dashed line? Because I only see pink near the critical point.
I mean, for the G larger than 0 region, it converges super fast. Like for lambda equals 4, it is already indistinguishable from the analytical solution. But for G smaller than 0, that is the unstable potential region, the convergence of the upper bound is very close. But you see the convergence of the lower bound, they are still very quick to the analytical solution. This is the overall structure.
What is the interpretation for negative G from the integral point of view? Is it analytic continuation, or what is, how should we understand it?
No, okay, you go on, but I can also say something.
Yes.
Because okay, you want to explain, or I will say?
Yeah, this is because I just explained that for the large N matrix model, the tunneling effect, it is exponentially suppressed. So if we have a deep enough local minima, the tunneling effect is we still have some sensible model actually.
I mean, there is still like a minimum around 0, but then it can tunnel outside, but this is suppressed.
Yeah.
So there is a critical value when it's
when it is too the local minima is not deep enough, it can still tunnel off. Yes.
And it appears to be unstable already for negative G's. Like you have unstable potential already decaying at the infinity, but the eigenvalues never go to infinity because they are squeezed in this local minimum.
But okay, so is there a way to define the matrix integral, which like at finite and how does it exist, this phenomenon? How do you define this integral? Or just an analytic continuation? That's
no, by loop equations. Loop equations define everything. We solve loop equations with positivity condition.
Yeah, I understand. But if we add finite n, does the negative G make sense, or it's infinite n effect?
No, doesn't make sense. I mean, we would find no such solutions, only for positive G. All this is good for planar limit.
Right. Thanks.
Okay.
Maybe some deformation of contour of integration assumes when
that, of course, that can help.
Yeah, so that's the standard thing for such integrals that you deform contour.
And why does it stop being defined? If I imagine you can deform, then it doesn't matter how small G. But okay, this will go into depths of matrix integrals.
But that's already matter of this particular resummation that's inside probably of this formula. So probably, I don't know.
Oh, no, for finite n, any negative G can be achieved by analytic continuation. But there is like Lachian limit, whereas for some G is good and for some G is not.
Yeah, so it's opposite.
Can I ask a question related to what Kolya said? How good is this method in detecting the critical points? Suppose you didn't know that G critical is -112. Would you be able to predict it by looking at?
Well, we will discuss it later in the two matrix model context.
But you see from the graph, it's quite well seen, because after beyond this point to the left on the graph, it diverges completely. So it's just the tip of this. You see, there is
yellow zone ends, right? Yellow zone ends to the for two negative G.
Not yellow, but rose. The best.
Yeah, but this one you can see almost.
Yeah, you can see already in yellow. But of course, it's not precise, and it's seen that the method works. The worst place for it, it's of course around this critical point, but still it works.
But if you're on the right side, I mean on the side where the solution still exists, so what happens to the approximants? Do they sort of, do you see the, how is it called, critical slowdown of convergence?
You mean where? On the right-hand side?
On the left, for negative G.
No, I'm asking about the right side. You know, where to slightly to the right of the critical point where the solution still exists. How? I mean, is it true that the method then starts to converge slower and slower
with lambda?
Well, I mean that.
No, I didn't. Sorry. Well, I didn't explore the too large G. I mean, for G, like G smaller than 5.
No. I think Kostya speaks about the negative G's, yes, but on the right from the critical point. Yes, if I understood it correctly.
Yeah. So the question is about the vicinity of the critical point where the solution still exists.
Yeah, you approach the critical point from the right. How? Why? You see that it works less and less well, the method, yes? You need larger and larger lambdas to get the same precision, yes?
Yes.
Yeah, it's clear from the picture.
But is it possible to quantify it in some way? Like to compute some critical exponents from the convergence rate?
I'm not sure.
Well,
I
you
mean,
only
the
get to
convergence-
lambda 8, so you can get some exponent, but it will be very unprecise, with only 5 points.
Yeah, the point is just to remind Zechuan, it behaves like G minus G critical. There is a singularity like G minus G critical to the power 3/2 for all this for this moment. Can one really distinguish this 3/2? But there are also regular terms. And, it's difficult to distinguish. So you have to differentiate, as we know, 2 times to make it divergent. Then the second derivative in G of W2 of this second moment will already have singularity precisely at this point. And maybe then it's better to, can we notice that it behaves like 1/square of G minus G critical? That's the point.
So could I ask an unrelated question? So the planarity enters when you wrote loop equation, this product term in the right-hand side, rather than expectation value of double trace is just a product of single traces. Is it where you do a large n approximation?
Yes, exactly.
And then can you go 1/n? Because like as far as I remember, you can extract 1/n expansion from loop equations. So how?
Yeah, in principle, it's possible.
Okay, thanks.
Okay.
By the way, Kola asked a question, maybe you didn't answer, it was not a complete answer on your side, Zechuan, about why we are sure that this increasing lambda we will get exact results. If lambda equals infinity, we will get to this. Maybe you will comment about the hamburger problem, which you taught me once.
Yeah, we are going to discuss it.
Ah, you will discuss it. Okay.
Yeah. Okay. So let's look at the non-convexity a little bit. This is for the same model, but with mu equals -1. So this is negative quadratic coefficient. So this is actually a double well potential, which admits a continuous spectrum of exact solution. In this case, we see that the analytic solution, they are curly curves, and the allowed region in terms of W1 and W2, they are highly non-convex. So we can see the non-convexity of this problem very, very easily. For the let me remind you that we have 2 problems to solve. The first one is we need to justify this positivity condition. And the second one is non-convexity. For the first problem, we propose to we deal with this problem by analytically solving this bootstrap condition. So we first note that our loop equations, they can be all these information, they can be encoded very compactly into some conditions on the resolvent function. How to do it? Let's look at equation 31. If we sum over all the k's in terms of z to the maybe z to the minus k minus 1, and we will get a quadratic equation on the resolvent function. The remaining part, the GW2 plus GZW1 part is from the collecting of the tails of the formation. So because the G is the resolvent function, there are some formal power series. So actually this quadratic equation, it contains all the information from the loop equation. If we could encode all the information from the positivity of correlation matrix into the resolvent function, then we are basically done. This is transformed into a complex analysis problem, and maybe we can solve it. Luckily, this could be done by using the result of the solution of hamburger moment problem. What is this this theorem? Let me describe it very non-rigorous but very easy way. That is, we are given a series of real numbers, we are asking that does there exist a positive Borel measure on the real axis such that this series of real numbers, they are just the moments of this Borel measure, positive Borel measure. Actually, this is actually we have an equivalent condition, that is the Hankel matrix formed by this series of real number is positive semi-definite. And also we have some uniqueness conditions on this result. So the Hankel matrix is just our correlation matrix. So this indicates that our moments, there are moments on the of a measure on the real positive measure on the real axis. And this measure, I want to say that it is actually our eigenvalue distribution, but we don't really need it here. We just substitute the equation 35, that is the moments by the measure mu, into the resolvent function, and we came to the conclusion that this implies that the analytic function GZ is the eigenvalue distribution defined by it is only on the real axis and it's positive everywhere. So this by this way we transform all the information from the loop equations and from the correlation matrix into the resolvent. So we can solve it actually, and this actually by solving it by the complex analysis we can actually rigorously prove that the analytic solution is the only solution of all the bootstrap conditions. So it must converge to the analytic solution. And also the positivity condition, what does it mean? We now get the hint that it is contains the information on the sample space, because the loop equation, we know the potential, what it is like, but we don't know whether we are integrating over the Hermitian matrix or unitary matrix. But this Hamburger moment problem tells us that it is actually we are integrating over the Hermitian matrix. Actually, for different sample space, like the sample space of unitary matrix, we have a different kind of moment problem. That's called trigonometrical moment problem. And for more involved sample space, we have other moment problems that to deal with this problem. So we solved the first problem. For the second problem, do we take a break? Hi, do we take a coffee break or we still keep going?
So sorry, what's the question?
Yeah, you remind me before that there is a coffee break.
Yeah, you want to make a break? Yes, that will be perfect.
Yes,
yes, great.
We could make a break here.
Mm-hmm.
You'll need to unlock your iPhone first. I didn't.
Yeah, good. Then let's pause the recording.
Okay. For the non-convexity problem, let's just ignore it first, and we try some multi-matrix model to see what we can get. Then we will see that whether we really need to deal with the non-convexity problems here. Here we propose to study the following two matrix model. It is actually a quartic plus commutator square model. This model, to the best of our knowledge, for general G and H value, like G equals H equals 1, it is not solvable. But for for H equals 0, this is nothing but a two decoupled one matrix model. And for G equals 0, there is some analytical solution of it. So this is a very good candidate to test our method for the non-solvable problem, non-solvable matrix model. So we can compare our numerical result with analytical result. Here we pick cutoff equals 4. This is the lowest order where the quadratic loop equation appears. In the lower cutoff, there is only linear loop equation. At this cutoff, the longest operator has length 8. And we also know that this model has a D2 to the 3 symmetry. That is A to the minus A, B to the minus B, and A to the B. For simplicity, we assume all these symmetries. Actually, we can study the symmetry breaking case later. Up to this global symmetry with cutoff equals 4, we have 20 independent or non-equivalent operators. They are subjected to the loop equation, that's a total derivative. Here, there is only one quadratic term. So we denote it as Q for quadratic, which is trace A squared to the square, trace B square, and trace A squared to C squared. We have 14 loop equations. They are algebraically independent here. So this is all the 14 loop equations. We see that I put all the Q on the left-hand side. So you can see there is only 3 loop equations. They are quadratic, and all the remaining, they are linear. For the correlation matrix, it is very similar to the one matrix model. We just write the words in terms of A and B and take the inner product between the words to formulate a single trace operator. Here in the footnote, I denote that the inner product here means inner product of O1 and O2 is trace of O1 delta O2. As an example, this is for the even odd words correlation matrix. Because there is a global symmetry of V2, the big correlation matrix, it actually decouples to the even matrix, odd matrix, and even odd matrix. So this matrix and two other matrices, they are positive semi-definite. Okay, so we get all the conditions. All these constraints, they are convex, except the quadratic loop equation.
Sorry, could I see again the matrix?
Yes, this is for the even odd.
Yeah, why do you have a 4b squared twice on diagonal?
A4b squared.
Actually,
you can see here, even odd words, they are 5. So you can take the inner product between them, and they are identified through the.
No, then I don't understand the notation for the this trace. Is it without order or what is that? Why expectation value of A4b square is positive, for example?
You mean why they are there?
Like, so 47 for you will be positive definite. Do I understand correctly? Then all diagonal elements should be positive, right?
Yes.
So how do I see that trace of A to the 4b square is positive?
Yeah, here you see for the second one. Let's look at equation 46. For the second word, you just take the inner product of it, and you will get the trace A to the 4th C square.
Okay.
Yeah. So they are positive.
And then why does it appear several times? It also appears.
Yeah, because the trace of the inner product of the second word is trace A square trace A to the 4th B square. And the inner product of the 4th BAA, they are also trace A square B to the 4th because A to the B global symmetry.
Mm-hmm. So in this matrix, you take, so 47 is the result of, so you multiply O times O dagger, right? From this.
Oh, yes.
And then which group you take? There are 3 groups of operators for O. On the previous, you have this odd, odd, even.
Even odd, it's written.
So you have 44, 45, 46. These are already squares, or?
Yes. You need to take the inner product of them to formulate the correlation matrix.
So you take one of 44 times another one of 44.
No. I take the inner product of itself. Because the inner product between them, they are vanishing.
Ah, yeah, okay. So then you have several positive definite matrices.
Yes.
Okay.
There are, initially, they are big correlation matrix, but you can use the global symmetry to make it into a block diagonal one.
Okay.
Yes. Okay, let's go on. So we can expect that when we are considering higher and higher cutoffs, we have more and more quadratic terms. We must deal with quadratic term series. The most naive method is just we treat all the quadratic terms, they are independent variable. By this, I mean, let's look at this loop equation. We forget that Q equals trace A, the square of trace A square, but we treat them as independent variable. So effectively, here we are considering, instead of 14 loop equations, we are considering 13 loop equations. And they are, well, but this naive method works. It actually works, but we have better choice with better conversion. Let me show it. Let's consider a toy model again. There are only 3 quadratic loop equations: x squared equals p1, y squared equals p2, and xy equals p3. Here, the t is here we denote it as some linear combinations of some other variables. So x squared, y squared, and xy, they are the only quadratic terms. For the first one, instead of forgetting about x squared equals square of x, we can replace it by x squared smaller than p1. This is positive. This is convex. Why? Because we can write it in the positive semi-definite matrix form. It is of equation 49. For the y squared equals t2, we can reproduce the story. But for x1 equals t3, we cannot. Why? Because neither xy smaller than t3 nor xy larger than t3 is convex. This is because x squared and y squared, they are positive definite quadratic form, but xy is not, it's indefinite form. So to do tempting direction is that we consider the linear combinations of x and y. So we make some relaxation. But this is not it is not very elegant that we choose a grid of alpha on the real axis and like 10,000 grid. Here is actually a better choice. Let's look at the equation 50. We demand all the alpha, this equation to this inequality to be true for all the alpha. So this is equivalent to that we demand the determinant in terms of alpha to be non-positive. Or in the other words, we can massage the determinant into the equation 51. Yeah, into the equation 51, it is a determinant. So this combines with x squared smaller than t1 and y squared equals smaller than t2. We came to the conclusion that we can relax the initial non-convex equality condition to the equation 52 inequality condition. So we can finish our relaxation. For the more general case, our strategy is we isolate the quadratic terms from the loop equation into the form of equation 53, and we impose the relaxation matrix 54 to be positive semi-definite. Here we forget about equation 53 on x, but we impose the condition 54 on x. In our case, with our quadratic term q, this is equivalent to that. We forget q is the square of tree square, but instead we impose the inequality 55. So how does this work? Well, for generic value g equals 1 and h equals 1 under the cutoff 4, we get actually 1-digit precision on the prediction of trace A square. Of course, the result here is fully rigorous. We see that we already have a decent convergence here. So as we set all the conditions into a form of SDP, we can increase the cutoff, and we have very mature solvers for the SDP so that we can push the cutoff to very high. The highest result here is lambda equals 11, that we are considering the words of the operators with length 22 actually. We have a 6-digit here. The audience can also see that the shrinking of the allowed island actually when we are increasing the cutoff. We have finally at lambda equals 11, we have 6 digits. We can compare this result with Monte Carlo results on the same subject. This is some Monte Carlo results recently done by Raghav and Pedro. They got actually 3 digits on the precision of T2 and T4. Of course, this prediction falls into our rigorous bound of bootstrap. They are done this by the n equals 300 Monte Carlo simulation. This took 1 to 2 hours to convert. On the contrary, the bootstrap method from our code, it took less than 10 seconds to get the same 3-digit precision of the Monte Carlo result. So we believe that this is a very strong signal that bootstrap is a better method than Monte Carlo when we are dealing with larger matrix model. We can also compare our numerical result with the analytical result. Here, the result is H equals 0. That this is actually nothing but a 2 decoupled one matrix model. We see that at lambda equals 4, the result is already almost indistinguishable from analytical result. This is for the G smaller than 0, that's close to the criticality point. And for G equals 0, this model is also solvable. We have actually lower speed of convergence, but we see that maybe for lambda equals 7, we still have a very good convergence on the result, almost indistinguishable from the analytical result. And also for the negative G, we can explore the critical points and get a very precise estimation on the critical value. We can also, for generally, we can explore the phase diagram of this model. By phase diagram, I mean how negative G and H could be. We know 2 points from the analytical side. That is, for G equals 0, how negative H could be, and for H equals 0, how negative G could be. But generally, this should be a 2-dimensional curve, and we can explore it by the bootstrap method. Here, the gray region is rigorously excluded by our numerical bootstrap. And the blue region, it is the region that with stable potential, that is bounded from above. Bounded from below. So in this region, even for finite, and this is well defined. And the red point and the blue point, they are analytical boundary from the analytical result. So we see that green point and the red point, they are almost on the gray boundary. This is very strong signal that our gray boundary, they are very precise already. Okay, we see that our relaxation method, it generally works well. I have some remarks here to explain why it works well. First, the most important reason is that the exact solution of the model is a single point, so it is convex. The exact solution is convex, so our method makes sense. In the symmetry breaking case, there is the exact solution is a curly curve, so it is non-convex. Like in this case, we have already shown in the one matrix model. Through the relaxation, at most we can get a convex hull of the curly curve. So there is no way that it will converge to the exact solution. We need some additional tricks to deal with this symmetry breaking solution. But it seems we don't have enough time to describe the symmetry breaking case. So for interested audience, they could refer to our paper after our talk. Some other reason that the relaxation method works well is that the number of independent quadratic terms, they are actually very limited. You see, in the lambda equals 4 case, we have 14 loop equations, but we have only 1 quadratic term. This is general, that we have much more loop equations than the quadratic term. So by the relaxation method, we don't really relax the problem a lot. So lastly, the optimal solution of convex optimization problem, it mostly appears on the boundary of the feasible region. By this, we mean that the relaxed inequalities mostly it works as well as unrelaxed equality, because we are taking the maximization or minimization. So it always appears at the boundary. So the equality works almost as well as the inequality works as well as the equality. This happens a lot of times. So this is several remarks on why the relaxation method works. Okay, so we jump to the symmetry breaking part. For interested readers, they could refer to our paper. Here we make a brief conclusion and state some future direction. We see that the matrix bootstrap, it is an interesting alternative to Monte Carlo method to compute the functional integral. It gives the exact inequalities on physics quantities, and it is also efficient. In this work, we got hint that the positivity condition, it is actually contains its information about the sample space. And numerically, to overcome the non-convexity of the nonlinear loop equations, we proposed the relaxation method, and we tested that it works well. For some future directions, the first one is maybe the most important one is large N Yang-Mills theory on the lattice. There is already some previous work on this subject by Anderson and Kruczynski, but here precision is far from the precision of Monte Carlo. So we are still far from the result of Monte Carlo there. Probably with our relaxation method, it will work much better than the previous result. And for the correlation matrix, we are imposing all the conditions on the correlation matrix. I mean, the positivity of the correlation matrix is equivalent to that all its principal minors they are positive. But unlikely that all the submatrix contains equally amount of information. It is very likely that a small submatrix contains 99% of the information already. So it's very useful that we can come up with some ideas to select that some submatrix of a correlation matrix that they are much more important than the other matrix. Okay, that's finished my talk. Any questions?
Okay, thank you, Zechuan. We have time for questions. So in the end, you mentioned Yang-Mills, so maybe it's very complicated. Do you think is it possible to start do something in 2 dimensions?
In 2 dimensions, actually, we tried some. It works well. But you know, for 3 dimensions and 4 dimensions, it is much more involved. So we need some further ideas to simplify the problem.
I already asked many questions.
Yeah.
All right, let's stop the recording, please.